Let's get started. Stage 1 of the project is due now, so give it over. How have you got it? Is it printed out? Is it a digital file? You all use the same template, right? All right. So this is the group of Lambert, McMahon, Mallory, Kirk. Okay.
I'm going to email it right now. I was told it was due at 5. I didn't print out a copy.
The back of the page.
Did it say 5? All right. Well, if you want to take till 5.
5 o'clock today.
Okay. All right. Well, then we'll go with that.
So we extra credit or not?
Not numerical credit per se, but like the kind of credits that you could exchange on something like Caramel. Caramel credit, we'll call it.
Is the Wi-Fi down overall?
That's working on my computer.
The brain chip that connects to Wi-Fi isn't. I'm not reading a signal on that, so it might be. Yeah.
Dr. Whitney, how do I switch to administrator? I got like Chen on here.
So Control-Alt-Delete, switch user.
Okay, so switch user.
Yeah. So do that.
Oh, other user.
And then you can try yourself to begin.
Otherwise, administrator.
Yeah. Yeah.
Is that with a capital A or just lowercase?
I don't know.
Okay.
I think it's lowercase. All right, I'm going to give you homework 3 at the end of class today, and it'll be due at the beginning of class on Tuesday. So you have the weekend to go over that. So we're going to be talking about culverts today and using HY8. So the first thing we're going to work through is this example. And if you've already logged in, start up HY8, and in the meantime I'm going to try and help everybody make sure that they're logged in. We'll try and get on the same page with the program running, and we'll talk through it together. All right, we're going to begin with an analysis problem. And this is a really simple one, like the demo that I worked in class on Tuesday. This is going to be, I guess, maybe even simpler because it's a box culvert. The N value of 0.013 would suggest that that's probably a concrete box culvert. We're given the slope, but remember, you don't actually enter the culvert slope in. If you recall back to the demonstration, the way that you tell the program how steep the culvert's laid out is that you specify the invert elevation upstream and downstream. So we're actually going to have to do just a real quick hand calculation to find out what slope we need to use. Now, it's 40 meters long from inlet to outlet, and we expect a headwater elevation 2 meters above the invert elevation. Now, we don't actually know the absolute elevation of the inlet or the outlet. All we know is the slope. And so what we're going to do is just select some hypothetical elevation datum to start everything off with, and then we're going to make the headwater elevation relative to that datum. We'll have the outlet elevation relative to the datum. So for example, what we could do is we could say that the outlet invert is elevation 100, and then the inlet would be 100 plus whatever the slope is. And so let's work that out on the board. Sometimes it helps to have a sketch before you start cramming numbers into the program, a sketch that shows the elevations and everything worked out. Okay, so we have a channel that's sloped at 0.007, so 0.7%. Here's the box culvert, and I'm going to just define as my datum the outlet invert. I'm going to say the elevation of that is 100.00 meters. All right. I haven't handed, oh, yeah, the handout. Yeah, you've got that, right. I thought you'd grabbed the assignment. Okay, so if the slope is 0.7% and the length is 40, for 40 meter length, then that will make this elevation equal to 100 plus 40 times 0.007. And so the elevation is 100.28 meters. So that is this elevation. The other thing is we are going to have to assume something for the tailwater just to put it into the program. Let's assume concrete lined channel. So we're going to assign an N value of 0.013 downstream as well. Sometimes we have to think in terms of station. You know, the program asks for us to define lengths sometimes as stations, and so I'm going to say that let's call this station 2 plus 0, 0, and then the station here is 2 plus 40. And that's how we'll define the culvert length, is by the stations that we put into the program. All right. And let's find out if the channel width is 5 meters. So here in part A of the problem, it's saying for a channel width of 5 meters. And so this was all a cross-section of the culvert. Let's now look at a top view of what the area looks like. There is a stream, and the road goes over the stream, and there's dashes in the road, and we are assuming a channel width is 5 meters, is this distance here. Now we don't know, oh yeah, we do know that since the culvert itself is 40 meters, we're going to say that the top width is 40 meters as well, because remember, we're treating the top in such a way that it can assume that there's overtopping and it's a broad crested weir. So I think that's all the geometry we have to understand before we can start putting things into the program. Go ahead and turn on HY8. Create a new culvert, start a new project, and add a crossing. Okay. The range of flow rates is the first thing. We want to find out what range we're going to be simulating over, and we don't have any idea yet what range of flow rates should be simulated. So we're going to be guessing blind. We're trying to find the flow rate that will cause a headwater depth of 2 meters. And so to begin with, we're in cubic feet per second, so I need to cancel that and change your units to SI. If you already have your units in traditional, and switch it back. And we're going to put in a new culvert crossing. So this little button here for new culvert crossing, since I canceled out the one that I had before, I'll click new culvert crossing, and now I can see it's in cubic meters per second. So first time around, maybe I'll just have the design flow be 40, maximum flow 50. We'll just go from 0 to 50 and see if that headwater depth of 2 is somewhere in between there, and then I can rerun the simulation over the narrower range that I'll sort of hone in on the answer and then run it again. Okay, we have to define the tailwater, and this is a rectangular channel, and that's what there is by the default. We assumed a channel width of 5 meters. Well, we didn't assume it was given in the problem statement. Channel width of 5 meters. Okay, so put in bottom width 5. Channel slope, we'll use that same as what the culvert slope was. We'll just match the channel downstream to the slope of the culvert, which was 0.007. And the N value for the channel, we said that it's going to be concrete lined as well, so 0.013. And the channel invert elevation is where it's asking if it should match up the channel with the invert of the culvert. So the simplest approach and probably most common is just to match the two and have the elevation of the channel downstream be equal to 100 meters. And so we can click this and it'll calculate the rating curve for us. All right. And now we have to define the roadway. Remember, the option difference between constant roadway elevation and irregular is that an irregular would be used if you had a sag curve of the road going over the culvert. And so if the road was like this, no, that's not right. It's actually the other view. It's when you're looking at the face of the culvert that the sag would be definitive. And so if we had, here's our channel, and the road is going over the top, and here's the culvert barrel. So this would be a constant roadway width, or if we had a sag curve, then we'd specify irregular, and we'd start defining the points of that curve so that the overflow length increases as the headwater goes up. Constant roadway elevation, the width of the weir is always going to be the same. So we'll leave it at constant roadway elevation. And the first roadway station, that's where we are going to be defining how long the first roadway station, actually, it doesn't matter. That field can be left blank. I don't even know why it's there. But crest length is important. For this, the crest length would be 5 meters since it's a rectangular channel. And the crest elevation, we need to look back at the information that we've got. It's not actually going to overtop during our simulation. We're just going to go from no water up to a headwater of 2 meters. And so all we need to do is put the crest higher than 2 meters. We don't even know what the elevation of the roadway is. So we don't know what this elevation is. But for the simulation we're going to do, all we have to do is make it at least 2 meters higher than the 100.28 elevation of the invert there. So let's just make this elevation be 105, just so that it's high enough that overtopping doesn't occur prematurely. Crest elevation 105. It's paved on top of the road, and the road is 40 meters wide. Okay, now we get to put in the information about the culvert. It's not circular. We have to switch this over to a concrete box because it's a concrete box that's 1,500 millimeters by 1,500 millimeters. Okay, so the span is 1,500 and the rise is 1,500. We'll leave embedment depth blank, and the end value of concrete that we used was 0.013. It's got 0.012. Let's just change it to 0.013. It's a little bit more conservative to assume it's not going to be quite that smooth. 0.012 is a good estimate for new concrete that's been installed by a contractor who's really careful, but we'll assume it's maybe a little bit older and eroded a bit, or maybe the finish was slightly more rough. Inlet edge condition. Now, these are related to how much energy loss there's going to be. We don't have any information about if it's got a wing wall that's guiding flow in towards the culvert. These would improve the capacity of the culvert. And so what that would mean is the headwater elevation is going to rise faster if we don't have these wing walls. And in an analysis like this, we want to know what flow rate will cause the headwater depth to be 2. And so do we want to know what would be the safer thing, to assume that it's got wing walls or that it doesn't have wing walls? It doesn't. And so let's plan for the worst case scenario. Maybe in design you'd want to go the other way. You'd want to try and find the design that allows the greatest capacity for a certain headwater depth. But we're sort of looking at the other side of the coin in this analysis. And so we'll assume, rather than beveled edges with wing walls, we'll just say square edge 90-degree head wall, because that's the configuration that's going to induce the most turbulence and have the lowest flow rate per headwater depth. No inlet depression is fine. Remember, the inlet depression is the feature that is a little bit of an excavated section before the mouth of the culvert to allow for trash and sediment collection. Now we have to define the culvert's length. And so the inlet station we set up at the top there, we'll just call it 200 for the inlet station, and so therefore that would make the outlet station 240 if we want the culvert to be 40 meters long. And the inlet elevation of 100.28 is what I had calculated when I started with 100 at the outlet, and then I wanted it to be 0.7% over the 40 meters of length. Has anybody got questions on why a field is a certain way, or any confusion before we have it analyze the crossing? Bert, what's the purpose of this analysis? Like, why are we using the program in this case?
So we can tell how much flow we'll be able to make where that'll I guess.
Okay, so you're right. We're going to be trying to find flow versus something. We're trying to define the relationship of flow versus what? Headwater depth. Good. Okay, so we click Analyze, and this is what it gives us. Headwater elevation versus flow rate, discharge. And now, it's a little, I should have maybe picked a different datum because it's starting, the headwater elevation of 100.28, that is basically zero depth. And we're looking for what flow rate causes the headwater depth to be 2. And so 2 meters above 100.28. So what we're really looking for is 2.28. And so it looks like the flow, I had it analyze the flow rate from 0 to 50. Well, I didn't need to have that wide of a range because it looks like we're over that at a flow rate of 10. So instead of doing 0 to 50, let's close this and have it do, just double click on the culvert. Let's have it redo the analysis from 0 to 10. And you can have the design flow be 8. Analyze it again. And so now you can see that those 10 data points, instead of being from 0 to 50, are from 0 to 10. And that gives us a closer idea of what happens, like where is 2.28. And so it looks like it's between 5 and 6, right? We're looking for what is the flow rate that causes the headwater depth to be 2. Now, why 2? Maybe that corresponds to some soil pressure, to the pressure of water that's going to start seeping through the edge of the compacted fill that's there. You know, maybe there was analysis done on whatever fill is being used on the properties, and we know the water pressure that can be resisted safely, and that corresponded to a depth of 2 meters. Who knows why? Doesn't matter for us. We're just trying to hone in on at what flow rate was it 2.28. So it looks like it's between 5 and 6. So we can actually say, we'll go back to this, have the minimum flow be 5 cubic meters per second and the maximum flow be 6, and it will do 10 different flow rates between them. And we'll say, I don't know, 5.9. It doesn't matter what this design flow is. It does the analysis over the range of minimum to maximum. So analyze crossing, and you see from 5 up to 5.9, and it looks like the 2.28 is between discharge of 5.6 and 5.7. And so let's get crazy about it. Let's do from 5.6 to 5.7. Okay, double click here. 5.6 to 5.7. Analyze. 2.28. All right, so now we can say with authority that it is going to be Q is equal to 5.67 cubic meters per second when the headwater depth is 2.00 meters. And so headwater depth, when the water is at 2.00 meters, then the elevation of the water was at 100.28 plus 2, so 102.28. And that's why I was looking for, the first time that it says over here 102.28, I was looking for the flow rate that goes along with that. Okay. Before we move on to part B, let's just play around on part A a little bit. Remember, we were talking about how we'd assume worst case scenario with a square-edged face, not putting in wing walls. Let's see how much would it drop the headwater depth if we did have a nice smooth transition zone. And so let's change the culvert configuration. Instead of having a conventional inlet and inlet edge condition being square edge 90-degree head wall, let's just try a, let's see, 45-degree flare wing wall. And analyze the crossing again. Now we may need to change these flow rates because maybe it's not going to still be between 5.6 and 5.7. Let's have it go from 5 to 6. Okay, so all we did was we changed it from square edge 90-degree head wall to 1-to-1 bevel 45-degree flare wing wall. All right, so analyze crossing. Now, where does it get to the 2.28? It's actually above 6. So I'm going to have to close this and change the analysis to be 6 to 7. Analyze it again. So that 2.28 we're looking for looks like it's between 6.2 and 6.3. So we're honing in on it. 6.2 and 6.3. Analyze crossing. Okay, so 6.25. So this other analysis that we just did, so it's Q, and this was 45-degree wing walls. Q was 6.25 cubic meters per second for the same headwater depth. So you're able to pack a little bit more flow through the culvert if you've got that transition zone there. Any questions? Yeah.
So, well, what exactly does that do? Is it kind of like the orifice thing, like it's reduces the energy loss or something?
All right. Good question. In this case, it must not be just strictly, let's first look at this figure. And so it's some sort of a transition that's guiding the flow. I guess it's more like this. So instead of just being a pipe sticking out of a hill, these wing walls guide the flow. And if you remember back to the labs that we did during fluid mechanics, think about pipe bends. And so a gradual pipe bend had less pressure loss than a sharp 90-degree pipe bend, because the 90-degree pipe bend induced a lot more turbulence as the flow was changing direction rapidly. In this case, having the wing wall is having the water change direction more slowly as it enters the pipe. Now, that wouldn't matter. That can only matter depending on certain conditions. And if we go, where are those slides? Showed different conditions, yeah. So it's conceivable that there would be a case if the headwater was totally submerged and the pipe is only partially full, it may not have as much of an impact. I mean, so we saw that it went from 5.67 to 6.25. I don't know. That's maybe like a 15% improvement. It's not always going to be a 15% improvement under every condition. It probably varies depending on how deeply submerged the orifice is. Yeah.
Is the bevel head wall where it's mitered into the roadway and the bevel, or the bevel wing wall where they're above?
So you're asking about the different options in the program?
Yeah.
I don't know all those different options. So let's go to the list. So this one. So what was your question?
Is the bevel head wall where it's mitered into the roadway and the bevel wing wall?
So mitered, probably, yeah. I don't know. We could Google it and find out. And actually, you know, now that I mention it, now that you mention it, I think that there is a help manual that shows diagrams of all the different inlet types. So if we search for inlet, we might be able to find those inlet type. Yeah, it's got some drawings that can help us understand those, and I think it's maybe even more detailed than those. So if you come across a situation that's, you know, in the field, it exists, and you want to actually represent it as accurately as possible, then you can go and try and find which one is closest to, which one in the program is closest to what you see in the field. Oh, there it is. Yeah, you just click on the little question mark next to it, and it pops open the different options here. Mitered, wing walls, beveled, and so on. All right. The second part of this example asks the question, what is the channel width that causes the tailwater depth to be 2 meters for the flow rate found in Part A? Okay, so what we want to do is we want to have, when the flow rate is 5.67, how wide should the channel be downstream in order for the tailwater depth to be 2 meters? Okay, so the key to that is iteration with the tailwater rating curves with various channel widths. Let's go back to the program. Now, we can run the calculations for the tailwater completely independent of what's going through the culvert. So these calculations, just by clicking View, I have it run a set of calculations. They are independent of what's going on with the culvert. What I do need to do, though, is it's only going to calculate the tailwater over the range of flow rates that is specified up above here. So I want the range to be between 5.6, well, let's do it from 5.66 to 5.68. Therefore, what I'm doing is I'm forcing it to do a bunch of calculations at the flow rate that I'm interested in, basically. And we're going to run this, and we want the tailwater depth to be 2 meters. And so what is the tailwater depth? It looks like the tailwater depth is, since the elevation of the invert downstream was 100, the tailwater depth in this case is 0.373 meters. And so we can make the channel narrower. What this question is asking is, play around with various B. B is channel width, if you remember back to hydraulic engineering. So let's adjust the channel width downstream, the bottom width. You know, if it's 4, View, that's bringing it up to 0.4 meters. 3, View, 0.5. We can make this a pretty narrow channel, and the elevation still isn't to 2 meters. 1, have it calculate. We're getting close now, 1.66, 1.1. That's odd. Oh, I just made it wider. That's not odd. That's normal. Okay, 0.9. Okay, we're getting close, 0.85. All right, and there we are. We're just over. So maybe 0.84. And we're finding what channel width. That was the wrong direction. 0.86. Getting real close. 0.87. How wide must the channel be? And there we are. The channel width of 0.88 now is making the elevation of the water downstream equal to 2 meters. Okay. And this is just Manning's equation. It's running the tailwater calculations independent of what's happening in the culvert. You know, there may be some non-uniform flow for a bit as the water comes out of the culvert. Things are going to be a little bit weird for a while, but then the flow will become uniform again as it goes to the normal depth that's downstream. All right. So we've just done that first example there. What I'd like you to do is on your own try and solve this example too, design of a culvert. So we have a trapezoidal channel, and that helps to sketch this out on paper. You know, like what is a trapezoidal channel going to, what are the implications of that with respect to the culvert? So there's a front view, a side view, and a top view. And I'll draw what we had for the rectangular channel, and then maybe you can have similar drawings for this trapezoidal. So we had a front view. The front view for the example we just worked was there was some channel that was 5 meters wide, and we had a rectangular box culvert that was 1.5 meters by 1.5 meters. And I said that the elevation here was 100.28 meters. This was our front view, and then we just arbitrarily set this elevation was equal to, I think, 105 meters, and that made the weir length was also 5 meters since it was a rectangular channel. And then the side view that we had is the one that actually shows the culvert and the roadway on top of it. And so that we had here was the elevation of 105 meters. This elevation was 102.28. That was 100.00. The length was equal to 40 meters. And then the top view showed a river with a road going over it, and the road was 40 meters. It was 5 meter wide channel. You know, here we had underneath was the culvert. So translate, you know, come up with those 3 different kinds of views for what's described in culvert example 2. Try and put all the dimensions on that you can calculate, and design culverts under both of the situations that are described there. One where the headwater maximum that's allowed would be 7 meters above the invert upstream, and the other where you are allowed to have 1 cubic meter per second of overtopping. The fact that it says 8 meters from the bottom of the channel up to here tells you that if you're using the same elevations of 100 here and 100.28, then that means that the roadway elevation is going to be 108.28. And so for the second part of that problem, then what you want to do is you want to see 1 cubic meter per second going over the roadway, and then 9 cubic meters per second going through the culvert. Okay, let's talk briefly about getting output. I've got some crossing right now, and there's a button here that is Create Report. And if you click on it, it gives you the option of what fields, what information should be in the report. And you can see there's a lot of different options available to choose from. This is just the default. And so I need to browse to a location that I can write a report to, and it can either do it RTF, which is something that would allow you to open it up in Word. If you make an RTF format, then that's essentially editable, whereas PDF, the pages can't be edited, so you're not going to have the option to cut fields and make changes. So let's take a look at what a PDF looks like, and then maybe we'll try RTF in a second. These are just the default options here. If I click OK, then it builds a report, and it doesn't automatically open it. Or maybe it does. Yeah, it does. All right, there it is. You'll notice it's 9 pages long. So I'm going to give you a homework assignment in a minute, and you're going to do your calculations, and you're going to find your answers. If then you just printed out this and stapled it together and said, here's my homework, then I'm going to say, all right, so it's my job to sort through these 9 pages and go find the answer to the question. And I'd be a little bit irritated about that. Or the grader. Actually, we do have a grader this semester, so I'm not going to have to do that. My point is what I'd like you to do is not include a bunch of extraneous tables. Only include stuff that's relevant. And when answering the question, maybe you could write problem 1 at the top of the pages that correspond to problem 1, and problem 2 at the top of the pages that correspond to problem 2. And if it's asking what is the flow rate that corresponds to a certain headwater elevation, you'd take your pencil on the report and circle it. And underneath it, write, this is the headwater elevation that corresponds to a flow rate of, and then whatever it is. So making it very clear what the answer to the question is, and not just an open-ended report that includes a lot of information that isn't the answer to the question. In fact, most of the data on the reports is for flow rates and headwater elevations other than the answer that is being asked for. So I just wanted to give you that note. Let me hand you the homework now, and I think many of you have already finished the example, and if you'd like, you can start breaking down this assignment, doing the sketch for it and trying to translate it into HY8 speak.
Would you prefer to just do screenshots of the real data?
Screenshots is great, and in fact you do have to do a screenshot of the input information. So what you type in is going to have to be a screenshot. As far as the output information, you can do screenshot or report. But either way, even if it's a screenshot rather than a report, I still want you to indicate with your pencil what is the answer so that I know that you know the answer. Okay, before you go, let's just take a final look at the announcements here. The submissions that you've given me today, or will give me by 5 o'clock, I'm going to look over those in the coming days and try and get a sense for what data you've got and where the gaps might be. I'm intending to give you comments on that in class on Tuesday, along with a write-up that describes what the next stage of the project is. And so when you submit homework 3 on Tuesday, I'll turn around and give you the next part of the group work that you need to do for the project. Now, since all of the surface data will have been collected, then we may be in a position where we can scramble the groups or combine them or reorient things, because now everybody's going to have access to all the surface data. But I'm going to have to think about the next stage, and I'll give you that description in class on Tuesday. So that's it for today. Please be sure and plug in the tablet when you're done using it, and let me know if you've got any questions on HY8.